Hey, good morning to you. Welcome to another edition of Weather Academy. I'm meteorologist Tom DeVecchio. My cohort, once again, Craig Flint, is back. And our discussion today, something that you and I said, perhaps we could
should have done this earlier.
Sometimes, well, I mean, hey, we're learning just like, how to handle the COVID. Now we're learning how to handle, I do college teaching. I don't do elementary school teaching.
Yeah.
So we're going to go, I guess, back to basics.
Yeah, we're going to kind of back it up a little bit, and we're going to kind of review a couple things that we've already talked about in terms of outer space, okay, and planet Earth, which we talked about, planets. But we're going to really kind of hone in on Earth and why this planet is so exceptional and how it sustains life as we know it. And that has a lot to do with the atmosphere.
Absolutely. Without it, we wouldn't be here.
Yeah.
Period, stop.
And the atmosphere is a broad term. There are several different layers of the atmosphere, which we're going to delve into today.
Absolutely. And, it's not just the air that we breathe, it's the weather that we experience. And we find the atmosphere even does other things that allow us to have life here on Earth.
Right. And just think about this for a minute. I mean, I always encourage people to just take a look up every once in a while. Do you know how much is going on above your head? A lot. Every day. Let's start off with this picture. This is a satellite picture from the International Space Station, and that right there in the center is Hurricane Harvey.
Ooh, yeah.
Okay?
Okay.
But I notated it with little white arrows. You see that little thin blue layer? That's our atmosphere. It's very thin, and it's very delicate too. And it's almost like, you can come back here, and it's almost like a protective cocoon around the Earth. Okay,
that's a good description. It is.
So let's get started with the different layers of the atmosphere here, and really cool charts courtesy of NASA. I know they're kind of hard to read here on the chart on the left-hand side of your screen, but we kind of broke it down for you on the right. So as we talk about the layers of the atmosphere, we will go from bottom up to top, and we will start here with the troposphere. And Tom, you can take this
That's
one.
right, the troposphere. This is where most of the weather action occurs here. And on the left side of your screen, the troposphere, if you see that jet plane there, it's below that, okay? It encompasses about 7 miles, roughly, the depth of it, from the Earth's surface, and basically the bottommost layer, and that's where all of our weather exists. Some of the tops of storms may get into the stratosphere, but this is where it all goes. Mount Everest reaches near the top of the troposphere, so kind of give you an idea of just how thick it is. And as mentioned, some planes will fly on top of it. But this is where it's all happened. Roughly 99% of our atmosphere is in the troposphere. And the reason being is, just like gravity keeps us on Earth, it keeps our atmosphere, it pulls most of the atmosphere closer to the surface. So while the troposphere is only about 7 miles deep, that's really not all that thick. All the density of the atmosphere is right here.
Yeah. And that 7 miles is about average. Sometimes it varies a little bit. It can go a little higher, it could go a little bit lower. And speaking of Mount Everest being near the top of the troposphere, that's why you need oxygen.
Yes.
Because as you get higher, the particles in the atmosphere become less and less. So it makes it harder to breathe. And a couple of other quick notes that you made, Tom, about thunderstorms. It's really cool to see, like occasionally if you get a strong enough updraft with a thunderstorm, you get an overshooting top, which can poke into the lower layers of the stratosphere, which is the next level.
Right.
But check it out, though. Next time you see a big towering thunderstorm, and you see that cloud building up into the sky, and then you see the flat part of it at the top where it kind of fans out, that's an indicator that it has hit the top of the troposphere. And you can see that with your naked eye right from here on Earth.
Yes, you can. Yeah, we call it it's the anvil, that anvil top. And you may question, well, how do we know? What is the difference? Typically, the temperature in the troposphere typically decreases with height.
Right.
Now we have some little increases, we call those inversions, but the general trend is it gets colder from the Earth's surface to the top of the troposphere. Once you get to the stratosphere, we hit what we call the tropopause.
Right.
And the tropopause is when the temperatures in the stratosphere start to go up continually, and that's how we know that we've left the troposphere.
And we actually have an example of the temperature profile as we go up through the atmosphere, which we'll show you in a little bit. So next, in the layers of the atmosphere, it's kind of like a layered cake. So we discussed the bottommost layer of the troposphere. Let's move up the scale and talk about the stratosphere. Now, before you can get to the stratosphere, Tom mentioned a term called tropopause. Between each layer of the atmosphere, I want you to think about the term pause, okay? It's a barrier that separates each layer of the atmosphere. So before you can move into the next layer, you pause, okay? So I hope that kind of helps a little bit.
And keep in mind that barrier is, it's probably more like a covering of rubber. It's not like this solid brick. Boom, here we are, we're in the stratosphere. As Craig alluded to earlier, it can go up and down depending usually on the temperature profiles. But this isn't static. The atmosphere doesn't have strict boundaries.
Right.
Okay, it does tend to vary.
Okay, so stratosphere. Again, sometimes, especially the transcontinental airplanes, the big guys, will fly in the lower part of the stratosphere. This part of the atmosphere is where ozone production occurs. And ozone are little particles. And as Tom mentioned, the temperatures actually turn around and go the other way a little bit in the stratosphere. They actually warm with height. So that causes these ozone particles to sink through the stratosphere. Now there's really hot research right now and has been ongoing for a while. These ozone particles produce aerosols. And aerosols reflect sunlight back into space. So when you talk a little bit about, and I'm not going to venture too much down this foxhole, but when you talk a little bit about climate change, they study those particles in the stratosphere. So there's a lot of research going on with that right now. The other thing about the stratosphere, these are just a couple of key points. There's obviously much, much more, but I wanted to pick out the most important ones. In the stratosphere, there's no water vapor present, so no clouds, okay? And the top of the stratosphere from the surface of the Earth, where you and I are, goes up to about 31 miles from the surface of the Earth. Once you get to that 31 miles, again, you pause before you move into the next layer, which is the mesosphere.
There you go. And just one more note about ozone. As Craig mentioned, there's a lot of research going. Ozone, as many of you probably learned in school, is that protective barrier. Ozone, which is, for those who like chemistry, it's O3. Now, we breathe O2, oxygen molecule. The O3 molecule, by the way, it's toxic. Don't think, oh, there's an extra oxygen, we feel better. No, O3 is very toxic. But ozone protects us. It's a good absorber of ultraviolet light, so it does help protect us from a sunburn. But as Craig mentioned, we're finding ozone is more than just that.
Right.
And it'll be interesting to see where the research takes us from there. Mesosphere, very thin layer, the atmosphere. Now, particles burn up. The mesosphere is actually, it's a hot area. Now, keep in mind, when we say it's hot, temperature, and again, as you like to say, don't want to go down this foxhole too much, but temperature, temperatures in the mesosphere can hit very warm, even 1,000 degrees. You're like, oh my gosh. But the reason that we feel heat is because here at the surface is because the air is so dense, there's a lot of molecular action. We can feel the heat. When you get up into the mesosphere, it's 1,000 degrees, but believe me, you don't want to go outside in a spaceship because you will freeze. Because we measure temperature by the motion of molecules, not by how it feels on your body. So, this is the area, as the name implies here. And I know it's hard to see, but that's where a lot of the asteroids, you can start, when they burn up, they usually start burning up in the mesosphere. Now had a lot of clouds last night, so we didn't see it, but we're in the, what we call the Aquariid meteor shower. Unfortunately, we couldn't see too much of it.
Right.
But if you're looking, if you happen to see any shooting stars, the mesosphere is where you would find it.
Yeah, that's where you're seeing those shooting stars occur. And another real quick note about the mesosphere is, you know, Tom mentioned those air molecules. As you go up higher in the mesosphere, they become a little bit more spaced apart. So they're not close to each other. They're not rubbing up against each other to create that
heat that you can feel.
That you can feel, right. So as we continue to go up, this next layer is called the thermosphere. And this is an extremely thin layer of the atmosphere. And if you've seen the International Space Station flyover, that's where the ISS is located, in the thermosphere. Now there's a distinct line there called the Kármán line. And this is not a technical definition, but I want you to think of this as the quote-unquote gateway to space, okay? Now, the other cool thing about the mesosphere is the ionosphere is located within the thermosphere. And we're going to talk a little bit more about the ionosphere in a little bit. But that is basically composed of iron, okay? And if your dad's out in the workshop filing some metal or whatever, and you get those little metal shavings and you hold a magnet over them, what do? They react. They stand up. Kind of the same idea of what's going on in the ionosphere. We'll talk more about that in a moment. We have so little time and so much to get to.
Absolutely.
But that, so the thermosphere is where you get the space shuttle orbiting International Space Station. That's where the aurora borealis occurs, which again has to do with the ionosphere and the northern lights. And you can see the top of the thermosphere goes up about 440 miles from the Earth's surface. And again, before we get to the next layer, we have to pause. All right, so you hit the thermopause, and then we go up into the exosphere. And what I want you to think about, before Tom gives the explanation here, is exosphere, think exit. Go ahead.
Absolutely. And keep in mind, it's very nebulous where the atmosphere ends and, you know, the coldness of space begins. Craig did a good discussion there back in the thermosphere about the gateway to space. Generally speaking, you know, that Kármán line is considered, you know, once you get above that, the molecules are so far apart. They're still there, so we still technically have an atmosphere, but they're so far apart. And the exosphere, again, it's the edge. It's not a smooth one. It's not like an orange where, you know, you can find, you can follow it clearly. It's very difficult. But this is basically where your satellites orbit. The Hubble telescope that you may be familiar with is out that way. And you really need it to be in the exosphere because the molecules farther down tend to limit the ability of how telescopes can operate. You know, so it has to be above that layer in order for it to really work and give some of the awesome space pictures. And as you can see, the exosphere, 6,000 miles from the Earth's surface. So it's almost, it's about, I don't know my diameter of the Earth, the radius of the Earth, but it's almost like doubling the Earth. Yeah. It's like putting the Earth, it's about, the distance from the surface to the edge of the atmosphere is roughly the distance from the surface to the center of the Earth. And that is a long, long way.
Long ways. And as some of you who are a fan of Toy Story, if you're familiar with Buzz Lightyear, this is where you would say famously to infinity and beyond. This is kind of the beginning. You're way out there, and that is outer space for sure. All right, let's talk about some other quick examples here and some other things about the atmosphere. I told you I would show you the temperature trend through the atmosphere. So this is that yellow line, that squiggly yellow line is indicating what the temperature does, roughly, how it behaves as you go up through the atmosphere. So you can see the bottommost layer there, thermosphere, it falls with height. And then you get into the stratosphere, it starts to rise. and then you get into the thermosphere and it starts to fall again, and then you get up into the mesosphere rather, then you get into the thermosphere and it rises again. So that's just kind of a quick snapshot. So there's the rising through the stratosphere, and then it falls into the mesosphere, and then it starts to rise again as you get yourself up into the thermosphere. Running out of time here, but I want to quickly get to some of this stuff here. Aurora borealis. I mentioned the ionosphere. That is a real picture. The sky puts on one heck of a show at the poles a lot of the time.
Makes you want to almost move to the North Pole.
I've never seen it. I've never seen it in person.
No, nor have I. Might have seen it once, but others, again, see it all the time.
Yeah, so that's kind of an example of what an aurora looks like. Remember those little metal particles I was talking about? They're reactive in the ionosphere. And what this does is it actually kind of moves through the sky. And it's really cool. I'm sure if you went on to YouTube, you can see how these northern lights behave. A lot of that has to do with the solar winds. So you can see on the far left-hand side, and I know I'm going a little fast here, the sun. And then I've got arrows indicating the solar wind, which basically, if you remember back to a couple lessons ago, think of the sun as burping. It's kind of belching at us. And that sends that solar wind flying towards Earth, which is that little dot there on the right-hand side. And there's technically one more sphere called the magnetosphere. That is a protective barrier too.
Absolutely. And the solar wind is basically charged particles, some plasma and charge. So it's not wind like we feel on Earth. It's a movement of charged particles that react with the magnetosphere. And that's what gives us those beautiful colors.
So basically inside the Earth, there's a huge iron
core
that spins around. And what that iron core does is it sends out a magnetic field thousands and thousands and thousands of miles into space. And you see those yellow lines near the Earth there on the right-hand side? Notice how they're kind of warped to one side, to the right of planet Earth. That is because of the constant buffering of that solar wind on the left-hand side of the planet. But notice how they all kind of congregate towards the poles. And when they congregate towards the poles, that energy from the sun turns into the northern lights, which is, as we back up here, what it looks like right there. So that's a really quick explanation of the solar wind and the aurora borealis. It's really hard to get the northern lights down to these latitudes. Occasionally, if you get a strong enough solar storm on the sun, and X-flare or whatever it's called.
Yeah, and
Class 2 X-flare.
And if we get clear enough skies to actually see it in the wintertime, it's tough because we are so overcast in the winter as well.
Yeah. So that's kind of what it looks like with the aurora borealis. And I think what we're going to do is, since we are out of time, we'll have to leave it there.
Okay.
I wish I could explain this a little bit more. Maybe we could revisit this.
Perhaps we can a little bit next time.
Down the road.
Next Monday, maybe.
Yeah. But I just wanted to really quickly explain what the northern lights are and how the ionosphere, which again is a layer within the thermosphere, that creates this phenomena called the northern lights.
Yeah, beautiful lights indeed. And so there it is. The atmosphere, it's not just a bunch of air. It does a lot more than produce weather. It produces beautiful color like that. It protects us from ultraviolet rays and protects us really from all those other solar flares, meteors, they burn up. If not, we'd be the moon with all the pop marks on it. And, where would you build a house?
Right.
Is that meteor going to hit you?
Yeah.
So,
there's a lot going on above your head.
There really is.
And it's so important to life here on Earth, and it's like our little protector, our atmosphere.
So let's protect it
by
treating it as well as we can. Okay, we're out of time. So, but that doesn't mean you don't. You can still send us your questions.
Yeah.
Okay. And what inspires you?
Yes. Weather at WJET-TV.com is the email that you want to send your weather questions to, and keep chasing that inspiration no matter what it is. Maybe it's space and you want to learn more about space, or the atmosphere and you want to be weather dweebs like us.
Yeah,
That's okay.
Yeah, it's good. Look what it did for us. We turned out okay.
Yeah.
So far.
So far.
All right, thank you so much for joining us on the Weather Academy. Tom Atkins will be back. We'll talk more weather history going into the 80s with some of the big weather events then. So until then, for Craig Flint, enjoy your day.
See ya.